Shibboleth, shibboleth, shibboleth. Section 6.4, Pointers to Structures. To illustrate some of the considerations involved with pointers and arrays of structures, let us write a keyword counting program again, this time using pointers instead of array indices. As an aside, I would note that it's a classic early assignment in any programming language to do a word frequency program. Here is a Python program from my Python for Everybody course to count words from an input stream. Handle equals open parenthesis, single quote, Romeo.txt, close single quote, comma, quote, R quote, close parenthesis. Words equals handle.read, open paren, close paren, dot split, open paren, close paren. Counts equals dict, open paren, close paren. For word in words, colon, counts subword equals counts.get, open paren, word, comma, 0, close paren, +1. Print, open paren, counts, close paren. This section in this book implements a less general word counting program in C. The code depends on several functions from earlier in the book, and the code below is pretty complex, where the programmer only has access to low-level language without powerful and easy-to-use data types like Python's list or dict. It is likely that Guido van Rossum read this book, took a long look at this code, and designed the dict data structure in Python so the rest of us can write a data parsing and word frequency program in the above 6 lines of code without worrying about dynamic memory allocation, pointer management, string length, and a myriad of other details that must be solved when you're solving this program in C. Since Python is open source, you can actually look at the C code that implements the dict object in a file called dictobject.c. It is almost 6,000 lines of code and includes other files or utility code. There, thankfully, we only have to write one line of Python to use it. Counts equals dict, open paren, close paren. We will leave the complex bits to the C programmers that build and maintain. This section is not showing us how to use the Python dict object. Rather, it is showing how one would build a dict-like structure using C. So, continuing with section 6.4, pointers to structures. The external definition of key tab do not need to change, but main and binary do need modification. This is example on page 129 of the textbook, and that is available at www.cc4e.com/code. Pointer version of counting C keywords. Main, open paren, close paren, open curly brace, int t semicolon. Char word, open square bracket, max word, close square bracket, semicolon. Struct key, star binary, open paren, close paren, comma, star p, semicolon. While, open paren, t equals get word, open paren, word, comma, max word, close paren, not equal EOF, close paren. If, open paren, t equal letter, close paren. If, open paren, b equals binary, open paren, word, comma, key tab, comma, n keys, close paren, not equal null, close paren, p, right arrow, key count, ++. For p equals key tab, p less than key tab plus n keys, semicolon, p++, close parenthesis. If, open paren, p, right arrow, key count greater than 0, close paren, printf, open paren, double quote, %4d space %s \n double quote, comma, p right arrow key count, comma, p right arrow keyword. And now we look at the binary search. Struct key star binary, open paren, word, comma, tab, comma, n, close paren. Char star word. Struct key tab, open square bracket, close square bracket, semicolon. Int n, open curly brace. Int cond, semicolon. Struct key star low equals ampersand tab sub 0, semicolon. Struct key star high equals ampersand tab sub n minus 1, semicolon. Struct key equals mid. While, open paren, low less than or equal to high, close paren, open curly brace. Mid equals low plus high minus low divided by 2. If open paren, cond equals strcomp word, comma, mid, right arrow keyword, close paren, less than 0, close paren. High equals mid minus 1, semicolon. Else if, close paren, cond greater than 0, close paren, low equals mid plus 1, semicolon. Else return open paren, mid, close paren, semicolon, close curly brace to finish the while, and then return open paren, null, close paren, close curly brace. I do that when I have a typo. The typo in this case is the return null needs a space removed and a semicolon is missing, but I'll have to fix that. There are several things worthy of note here. First, the declaration of binary must indicate that it returns a pointer to the structure type key instead of an integer. This is declared both in main and in binary. If binary finds the word, it returns a pointer to it. If it fails, it returns null. Second, all the accessing elements of keydab is done by pointers. This causes one very significant change in binary. The computation of the middle element can no longer be simply mid equals paren low plus high, close paren, divided by 2, because the addition of 2 pointers will not produce any kind of useful answer, even when divided by 2, and is fact illegal. This must be changed to mid equals low plus open paren, high minus low, close paren, divided by 2, which sets mid to the point to the element halfway between low and high. You should also study the initializers for low and high. It is possible to initialize a pointer to the address of a previously defined object, and that is precisely what we have done here. In main, we wrote for open paren, p equals keytab, semicolon, p less than keytab plus n keys, semicolon, p plus plus, close paren. If p is a pointer to a structure, any arithmetic on p takes into account the actual size of the structure. So, damn it. A timer went off. Where was I at? Okay, let's start back at in main we wrote. In main we wrote. In main we wrote for open paren p equals keytab, semicolon, p less than keytab plus n keys, semicolon, p plus plus, close paren. If p is a pointer to a structure, any arithmetic on p takes into the account the actual size of the structure. So p plus plus increments p by the correct amount to get to the next element in the array of structures. But don't assume that the size of a structure is the sum of the sizes of its members, because alignment requirements for different objects potentially may cause holes in the structure. Finally, an aside on program format. When a function returns a complicated type, as in struct, key, star, binary, open paren, word, comma, tab, comma, n, close paren, the function name can kind of be hard to see and or find with a text editor. Alternately, another style is sometimes used. On 2 lines now, struct, key, star on the first line, and binary, open paren, word, comma, tab, comma, n, close paren. The spacing is mostly a matter of personal taste. Pick the form you like and hold to it. That's the end of 6.4. We'll edit it later. Okay. Shibboleth. Section 6.5, Self-referential structures. Before we start this section, a slightly longer aside from your narrator. Up to now, I have resisted the temptation to augment the book with my own bits of code. But we've reached the single point in the book where I feel there is too big of a conceptual leap between, not leak. Just start over. Just start over. Section 6.5, Self-referential structures. Before we start this section, a slightly longer aside from your narrator. Up to now, I've resisted the temptation to augment the book with my own bits of code. But we have reached the single point in the book where I feel there is too big of a conceptual leak. Leak! I did it again. But we have reached the single point in the book where I feel that there is too big of a conceptual leap between two sections. So I'm going to add some of my own narrative between section 6.4 and 6.5. The rest of this chapter talks very nicely about binary trees and hash tables, both essential low-level data structures in computer science, and both excellent ways to understand pointers, and how C can be used to build data structures like the Python dictionary. However, the author skips separately describing the structure of a dynamically constructed linked list, which is the first and foundational collection data structure in computer science, and should be understood before moving to tree and hash map structures. Linked lists form the foundation of the Python list object, Java array object, PHP numeric key arrays, and JavaScript arrays. The linked list can be dynamically extended, and items can be added in the middle efficiently as well as being pushed or popped on or off the front or back of the list. Linked lists are used also to implement queues as well as other aspects of operating system. I will attempt to mimic the author's writing style in this new section of the book. I'll write some sample code using a more modern dialect of C so it's easier to run on a modern compiler. Section 6.5.1, Linked Lists, Bonus Content. Suppose we want to read a file and print the file in reverse order. We don't know how many lines will be in the file before we read the file, so we can't simply use an array of pointers to strings and character arrays, like lines. In a sense, we need a dynamic array that grows as we encounter new lines. When we reach the end of the file, we then just loop through our stored lines from the end to the beginning so we can print them out in reverse order. One solution is to make a data structure called a doubly linked list of character strings. In addition to each line of data, we will store a pointer to the previous line and the next line as well as a pointer to the first item be add to the list, and then we'll call this the head of the list, and then the most recent item we've added to the list, which we'll call the tail of the list. We will see a singly linked list as part of the hash map data structure in a following section. A single linked list can only be traversed in a forward direction. A doubly linked list can be traversed either forwards or backwards. In previous code, given that our linked list of strings will keep expanding as we get new lines, we avoid hard-coding array sizes like pound-defined maxlen 1000 in the previous chapter. We were building a program to sort a file. Going back to the description of a line in our doubly linked list, it is clearly a structure with 4 components. Struct, lnode, open curly brace, char, 3 components. Going back to the description of a line in our doubly linked list, it is clearly a structure with 3 components. Struct, lnode, open curly brace, char star text semicolon, struct lnode star prev semicolon, struct lnode star next semicolon, close curly brace. This recursive definition of lnode might look chancy, but it's actually quite correct. It is illegal for a structure to contain an instance of itself, but struct lnode star prev declares prev to be a pointer to an lnode, not an lnode itself. We'll write this code in a more modern C dialect using modern memory allocation and I/O routines provided by the standard C library. This code is on page 130 of the textbook, available at www.cc4e.com/code. Pound include stdio.h, pound include stdlib.h, pound include string.h, pound define max line 1000. This is the length of the line, not the number of lines. Struct lnode open curly brace, char star text semicolon, struct lnode star prev semicolon, struct lnode star next semicolon, close curly brace semicolon. Now we have our main program to print the lines in reverse. And we will use int main open paren close paren because we're coding in a modern dialect of C. Open curly brace. Struct lnode star head equals null, semicolon. Struct lnode star tail equals null, semicolon. Char line, submax line, semicolon. While open paren fgetS open paren line comma max line comma stdin close paren not equal null close paren open curly brace. Char star save equals open paren char star close paren malloc open paren stirlen open paren line close paren +1 close paren semicolon. Stir copy save comma line. Struct lnode star new equals open paren struct lnode star close paren malloc open paren size of struct lnode close paren semicolon. New right arrow text equals save, new right arrow next equals null, new right arrow prev equals tail, and tail equals new. If head equals null, close paren, head equals new, semicolon. Close curly brace to finish the while. Now we'll print it all out. For open paren struct lnode star current equals tail, semicolon, current not equal to null, semicolon, current equals current right arrow prev, close parenthesis, open curly brace, printf, open paren double quote, s, close double quote, comma, current right arrow text, close paren, semicolon, close curly brace to finish the for, and then close curly brace to finish the main. Interestingly, if we wanted to print the list in forward order, or if we did have only a singly linked list, our loop would look as follows. For open paren struct lnode star current equals head, semicolon, current not equal to null, semicolon, current equals current right arrow next, close paren, open curly brace. Printf, open paren double quote, %s double quote, comma, current right arrow text, close paren, semicolon, close curly brace. In general, we use the variable names head, tail, and current, as well as next and prev, or similar names when writing code that builds or uses a linked list, so other programmers will quickly understand what we are talking about. After a while, reading a for loop to traverse a linked list becomes as natural as reading a for loop that progresses through a sequence of numbers. There's a typo here. What we are, let me just highlight it, and then I'll remember to fix it. There's a typo right there. So, okay, stop recording. Okay, so this is 651. Boy, 651's a long one. $652. Oh wait, is this six? This should be 652. Yeah, 652 binary trees. Okay. Let's see if I can do this one. It's a long one. It's a long shibboleth. 652. Suppose we, Section 6.5.2, binary trees. Suppose we want to handle the more general problem of counting the occurrences of all the words in some input. Since the list of words isn't known in advance, we can't conveniently sort it and use a binary search. Yet we can't do a linear search for each word that has arrived to see if it's already been seen. The program would take forever. More precisely, what is the expected running time? And it would grow quadratically with the number of input words. How can we organize the data to cope efficiently with a list of arbitrary words? Our solution is to keep the set of words seen so far sorted at all times by placing each word into its proper position in the order as it arrives. This shouldn't be done by shifting the words in a linear array, though. That takes too long. Instead, we will use a data structure called a binary tree. The tree contains one node per distinct word. Each node contains a pointer to the text of the word, a count of the number of occurrences of the word, a pointer to the left child node, and a pointer to the right child of node. No node may have more than two children. It might have only 0 or 1. The nodes are maintained so that any node in the left tree contains only words that are less than the words at the node, and the right tree only contains words that are greater. To find out whether a new word is already in the tree, one starts at the root and compares the new word to the word starting at that node. If they match, we found it. If the new word is less than the tree word, the search continues down the left. Otherwise, the right child is searched. If there is no child in the required direction, then the word is not in the tree. And in fact, the proper place for it to be is the missing child. This search process is inherently recursive, since the search from any node uses a search from one of its children. Accordingly, recursive routines for inserting and printing will be the most natural. Going back to the description of a node, it is clearly a structure with 4 components. Struct tnode, open curly brace. Char star word, int count, semicolon. Struct tnode star left, semicolon. Struct tnode star right, semicolon, close curly brace. This recursive declaration of a node might look chancy, but actually it's quite correct. It's illegal for a structure to contain an instance of itself, but struct tnode star left, semicolon declares left to be a pointer to a node, not a node itself. The code for the whole program is surprisingly small, given the handful of supporting routines that we've already written. These are getWord to fetch input and alloc to provide space for squirreling the words away. The main routine simply reads words with getWord, installs them in the tree with tree. This is the first example on page 131 of the textbook, which you can see at www.cc4e.com/code. Pound include stdio.h. Pound define max word 20. Pound define letter, single quote A, single quote. Main, open paren, close paren, open curly brace. Struct tnode, star root, comma, star tree, open paren, close paren, semicolon. Char word, sub max word. Char word, open square bracket, max word, close square bracket, semicolon. Int t semicolon. Root equals null. While open paren t equals get word, open paren word, comma, max word, close paren, not equal EOF, close paren, if t double equal letter, open paren, close paren, damn it. If open paren t double equal letter, close paren, root equals tree, open paren, root, comma, word, close paren, semicolon. Tree print, open paren, root, close paren, semicolon, close curly brace. Tree itself is straightforward. A word is presented by main to the top level root of the tree. At each stage, that word is compared to the word already stored at the node and is percolated down either to the left or right subtree by a recursive call to tree. Eventually, the word either matches something already in the tree, in which case the count simply is incremented, or a null pointer is encountered, indicating the node must be created and added to the tree. If a new node is created, tree returns a pointer to it, which is installed in the parent node. This is the example on page 132 of the textbook at www.cc4e.com/code. Pound includes string.h, struct, tnode, open curly brace, char, star word, semicolon, int, count, semicolon, struct, tnode, star left, semicolon, struct, tnode, star right, semicolon, close curly brace, semicolon. Struct, tnode, star tree, open paren, p, comma, w, close paren. We're going to install w at or below p. We've got a typo here. P should not be capitalized. Struct, tnode, star p, semicolon, char, star w, open curly brace. Struct, tnode, star t, alloc, open paren, close paren, semicolon, char, star, stir save, open paren, close paren, semicolon, int, cond, semicolon. If, open paren, p double equal null, close paren, open curly brace. We've got a new word. P equals T alloc, open paren, close paren, to make a new node. P right arrow word equals stir save, open paren, W, close paren, semicolon. P right arrow count equals 1. P right arrow left equals P right arrow right equals null. Close curly brace. Else if open paren, cond equals stir comp, W, comma, P, right arrow word, close paren, double equals 0, close paren, P, right arrow count, plus, plus. Indicate that we've seen the word one more time. Else if, open paren, cond, less than 0, close paren, lower will go into the left part of the tree. P, right arrow left equals tree, P, right arrow left, comma, W, close paren, semicolon. Else, P, right arrow right equals tree, open paren, P, right arrow right, comma, W, close paren, semicolon. Return, open paren, P, close paren, semicolon, close curly brace. And that's a bit of code. It's not much, and it's beautiful. Recursion is happening. The return P at the very end is really, really important because we're kind of always overwriting it, but we're okay. So but the overwriting works its way back up to the recursion because it's recursive, it's using pointers, away we go. Back to the text. Storage for the new node is fetched by a routine called talloc, which is an adaptation of the alloc we wrote earlier. It returns a pointer to a free space suitable for holding a tree node. We'll discuss this more in a moment. The new word is copied to a hidden place by stir save. The count is initialized and the two children are made null. This part of the code is executed only at the edge of the tree when a new node is being added. We have, unwisely for a production program, omitted error checking on the values returned by stir save and talloc. Tree print prints the tree in left subtree order. At each node, it prints its left subtree, all the words less than this word, then the word itself, then the right subtree, all the words greater. If you feel shaky about recursion, draw yourself a tree and print it with tree print. It's one of the cleanest recursive routines you can find. This example code is on page 133 of the textbook, which you can see at www.cc4e.com/code. I won't read the struct tnode code, just tree print. Tree print, open paren, P, close paren. Struct tnode star P, semicolon, open curly brace. If, open paren, P not equal to null, close paren. Curly brace, open curly brace. Tree print, open paren, P, right arrow left, close paren, semicolon. Printf, percent 4D space %S \n double quote, comma, P right arrow count, comma, P right arrow word, close parenthesis, semicolon. Tree print, open paren, P right arrow right, close paren, semicolon. Close curly brace for the if, and then close curly brace for the tree print function. Again, I agree with the authors, and that is one of the cleanest and most beautiful and most applicable uses of recursion that you will probably ever see in all your career. I'm not a fan of recursion in all cases, but you really can't do this any other way well. Back to the text. As a practical note, if the tree becomes unbalanced because the words don't arrive in random order, the running time of the program can grow too fast. As a worst case, if the words are already in order, this program does an expensive simulation of linear search. There are generalizations of the binary tree, notably 2-3 trees, AVL trees, and I would add balanced binary trees, which do not suffer from this worst case behavior, but we will not describe them here. Before we leave this example, it's also worth a brief digression on a problem related to storage allocators. Clearly, it's desirable that there only be one storage allocator in a program, even though it allocates different kinds of objects. But if one allocator is to process requests for, say, pointers to chars and pointers to struct T nodes, two questions arise. First, does it meet the requirement of most real machines that objects of a certain types must satisfy alignment restrictions? For example, integers must often be located on even addresses. Second, what declarations can cope with the fact that alloc necessarily returns different kinds of pointers? Alignment requirements can generally be satisfied easily at the cost of some wasted space merely by ensuring the allocator always returns a pointer that meets all alignment restrictions. For an example, on the PDP-11, it is sufficient that alloc always returns an even pointer since any type of object may be stored at an even address. The only cost is a wasted character on the odd length requests. Similar actions are taken on other machines. Thus, the implementation of alloc may not be portable, but its usage is. The alloc of Chapter 5 does not guarantee any particular alignment. In Chapter 8, we'll show how to do the job right. As an aside, by now you know that when the authors mention the PDP-11, they are sharing some aspects of the challenge of making C work on previous generation computers with short memory words and small amounts of memory, and at the same time making them work well on the incoming generation of computers with larger words and more memory. The research, thought, and care that went into making sure the C code was portable across multiple generations of computer hardware is on display in the previous paragraph. Back to the text. The question of the type declaration for alloc is a vexing one for any language that takes its type checking seriously. In C, the best procedure is to declare that alloc returns a pointer to char and then explicitly coerce the pointer into the desired type with a cast. Therefore, if P is declared as char star P semicolon, then open paren struct tnode star close paren P converts it into a tnode pointer expression. Thus, talloc is written as struct tnode star talloc open paren close paren open curly brace char star alloc return open paren struct tnode star close paren alloc open paren size of open paren struct tnode close paren close paren close paren. This is more than is needed for current compilers, but represents the safest course for the future. I would add that these concerns that the authors mentioned in this section are also nicely resolved in modern C compilers. In the NC version of C, they introduced the notion of the void type. The void type indicates the lack of a type, much like null is used to indicate not a valid pointer or not a flying toy. 1978, because the char type was generally the most native type on any system, it was often used as the generic pointer needed to return memory from an allocation function. In modern C, we use pointers to void and then cast the returning pointer, be a pointer to whatever struct or other data we just allocated. If we were writing alloc, the alloc routine in this book using modern C, it would return a pointer to void. The 1978 version is char star alloc open paren close paren, and the modern version is void star alloc open paren close paren. We've left the book alone. We haven't used void throughout the book, but it is a testament to the foresight of the authors that all the pointer casting code in this book still works today the same regardless of whether the memory allocation functions return char or void pointers to the allocated data. Got it. Made it. Just a couple of full screw-ups. Let me just check how my live stream is doing. Let's see how the live stream is doing. The code is 42. Of course, the code's 42. That's not really a spoil. Hello. Hi, everybody. Yeah. Okay. Yeah, so this was just a live, this is from where I record these things. It's how I record them. Let's see. Can I go back and record some more? Table lookup. Oh man, this is a monster. And it's not so bad. It's conceptually a monster. Okay, we'll keep going. We'll keep going. This is the hardest section of the book. Section 6.6, Table Lookup. As an aside, in this section, we finish our quick tour of the implementations of the 3 core data structures in computer science. 1, the linked list, 2, the tree, and 3, the hash map as described in this section. A singly linked list is also part of a hash map implementation, so you can compare it to the doubly linked list code introduced in the earlier bonus section 6.5.1. This section is worth understanding well because not only is it an excellent review of pointers and structures, but also because one of the most common questions on a face-to-face programming interview is, draw a hash map on the whiteboard and explain how it works. This is an easy question if you study and understand this section of the book, and almost impossible if you have not. In some ways, this section is the most intricate data structure that's described in the book. It is why it is so popular in coding interviews. Chapters 7 and 8 talk about lots of practical things like input-output of the Unix operating system. Elegant data structures and their use are core concepts in computer science. Understanding them highlights the difference between a good programmer and a computer scientist. In a sense, understanding how a hash map is the secret handshake of computer science. And it is the secret handshake because of this book and this section of this book, written back in 1978 and used in a course that the person interviewing you may have took when they were in college. Hash maps were difficult for them to understand back then, and so if you understand the concept, then you must be solid. So I hope you pay close attention to this section and remember the handshake. Back to the text. In this section, we will write the innards of a table lookup package as an illustration of more aspects of structures. This code is typical of what might be found in the symbol table management routines of a macro processor or a compiler. For example, consider the C #define statement. When a line like #define yes 1 is encountered, the name yes and the replacement text 1 are stored in a table. Later, when the name yes appears in a statement like in-word equals yes, it must be replaced by 1. There are 2 major routines that manipulate the names and replacement text. Install s, t, records the name s and the replacement t in the table. S and t are just character strings. Lookup s, searches for s in the table and returns a pointer to the place where it was found, or null if it wasn't there. The algorithm used is a hash search. The incoming name is converted to a small positive integer, which is then used to index into an array of pointers. An array element points to the beginning of a chain of blocks describing the names that have the hash value, And if it is null, then no names have hashed to that value. A block in the chain is a structure containing pointers to the name, the replacement text, and the next block in the chain. A null next pointer marks the end of the chain. Struct enlist open paren. Char star name semicolon. Char star def semicolon. Struct enlist star next semicolon. Close curly brace semicolon. The pointer array is just pound define hash size 100. Static struct enlist star hash tab open square bracket hash size close square bracket semicolon. The hashing function, which is used by both lookup and install, simply adds up the character values in the string and forms the remainder modulo the array size. This is not the best possible algorithm, but it has the merit of extreme simplicity. Hash open paren s close paren. Char star s semicolon. Open curly brace. Int hash val. For open curly brace, hash val equals 0, star s not equal quote, single quote, backslash 0, single quote, semicolon, close paren. Hash val plus equals star s plus plus, semicolon, return open paren, hash val modulo percent, hash size, close paren, semicolon, close curly brace. That's it. Now, it's got a typo in it. There's a /0. Let me highlight it just for my own sanity. A /0 where it needs a \0. Don't put that in the final thing, okay? As an aside, hashing functions. Hashing functions are one of the foundational notions. As an aside, hashing functions are one of the foundational As an aside, hashing functions are one of the foundational notions in computer science. Hashing functions are used for everything from high-performance in-memory structures, organizing databases, data, digital signing, network packet checksums, security algorithms, and much more. The above text is a really great example of a really simple hashing function. You should understand this simple presentation well so that when you encounter a more complex implementation or use of hashing, you can fall back on this text to understand that at its core, hashing is a very simple concept. So much of this chapter is a succinct example of some of the most powerful concepts in computer science. Please don't look at the 8 lines of code above and think, I got that, and just jump to the next bit. This chapter is showing you the way of the master programmer. Wax on, wax off. Be patient, slow down, and enjoy your time here. Back to the text. The hashing process produces a starting index in the array hash tab. If the string is to be found anywhere, it will be in the chain of blocks beginning there. The search is performed by lookup. If lookup finds the entry already present, it just returns a pointer to it. If not, it returns null. Here's the code. Struct enlist star lookup open paren s close paren char star s semicolon open curly brace struct enlist star np semicolon for open paren np equals hash tab sub hash open paren s close paren close square bracket semicolon np not equal null semicolon np equals an np right arrow next close parenthesis. If strcomp open paren s comma np right arrow name close paren double equals 0, return open paren np close paren semicolon return open paren null close paren semicolon close curly brace. It's very simple, very elegant bit of code there. Just note to self, move that code into, in this next code, into a file of its own. Back to the text. Install uses lookup to determine whether the name installed is already present. If so, the new definition must supersede the old one. Otherwise, a completely new entry is created. Install returns null if for any reason there's no room for a new entry. Struct and list star install, open paren, name, comma, def, close paren. Jar star name, comma, star def, semicolon, open curly brace, struct and list star np, comma, star lookup, open paren, close paren, semicolon, char stir save, comma, star alloc, open paren, close paren, semicolon, int hash val, semicolon. If open paren, np equals lookup, open paren, name, close paren, double equal null, close paren, open curly brace, i.e. it's not found, np equals open paren, struct, and list, star, close paren, alloc, open paren, size of, open paren, star np, close paren, semicolon. If np equals null, return null. That means the allocation failed. If open paren, np, right arrow, name equals stir save, open paren, name, close paren, double equals null, close paren, return, open paren, null, close paren, semicolon. Hash val equals hash, open paren, np, right arrow, name, close paren, semicolon. np next equals hash tab, open square bracket, hash val, close square bracket, second, semicolon. Hash tab, open paren, hash val, close square bracket, equals, nope. Hash tab, open square bracket, hash val, close square bracket, equals np, semicolon. We're actually pushing these new ones to the head of this singly linked list. And so those last two statements push the most recent top of the list forward and then replace with the new one at the top of the list. The list does not stay in any order. So we have a close curly brace to end all that if for the not found code, close curly brace, else, this is the already there code, free, open paren, np, right arrow, def, close paren, semicolon, free the previous definition. That's the string part of the pound define. If open paren, np, right arrow, def, equal stir save, open paren, def, close paren, equals null, close paren, return, open paren, null, close paren, semicolon, return, open paren, np, close paren, semicolon, close curly brace. So that last bit there was to, if you have a pound define with the same keyword and a different, later you have a different definition, you can replace the definition. And so that last bit was replacing the definition. Again, this code is pretty intricate. It's really both the hash table and a singly linked list going on at the same time. So take a close look at this on page 136 of the book. Stir save merely copies the string given its argument to a safe space obtained by a call to alloc. We showed this code in chapter 5. Since calls to alloc and free may occur in any order, and since alignment matters, the simple version of alloc is just not adequate here. See more in chapters 7 and 8. As an aside, one of the reasons that the authors make vague forward-looking statements whenever they talk about dynamic memory is that large-scale memory management in a programming language is still a subject of active research 40 years later. Back in 1978, it was absolutely not a settled topic. You can see this when the authors build a simple non-production memory allocation scheme with their own alloc and free routines backed by a fixed-length static extern array of characters. Dynamic allocation is essential to writing competent C programs, but it is likely that the production-grade dynamic memory support was still somewhat non-portable when the book was written. So they use simple, self-contained implementations in this book. Modern dynamic memory support is through the malloc, calloc, and free functions in the standard library. These functions request dynamic memory blocks from the operating system and manage those areas on behalf of your C code. On Unix and Unix-like systems, the memory allocation layer asks the underlying operating systems for blocks of memory through the SBRK interface. Even with virtual memory, programmers must carefully manage their use of dynamically allocated memory because memory is never unlimited. Okay. I think I need to go clean up the text and edit this stuff. Let me check the stream real quick. I doubt if anybody's really there. Come back, stream. Is anybody there? No. Hello, everybody. Yeah. Okay. Well, hi, everybody. I'm done with the recording. I got to sit and do some editing, but I only have my camera streaming, so you can't see all the editing. But I'm going to take these things and put them in Final Cut Pro, take out all the mistakes, and then go edit all the stuff that was in the book that I noticed, because I always notice mistakes in the book as I'm reading it. So this was an experiment. Wow, 51 minutes of live streaming of recording, and it's 20 to 5. So this probably will be the last thing I will record today. Let me know in the comments if you think I should do this more often. Cheers, everybody.